Hello and welcome to my talk. So I have to admit I have no sensor, so I'm completely wrong here, but I hope you find the talk interesting anyway. So my topic is Acoustofluidic, and in this case, Acoustofluidic tapping in structured microchannels using lateral modes of a transducer plate. And maybe I give you a short introduction to acoustofluidics. So acoustofluidics is the combination of acoustics and fluidics. In my case, it's microfluidics. Maybe one example nearly everybody knows is the macrofluidics in air, the acoustic levitation. If you have two speakers and generate the standing sound wave with high enough intensity, you can place light particles at the node points and they will stay there. And responsible for this is the acoustic radiation force. And for a standing plane pressure wave, it has this form. So it depends on a so-called acoustic contrast factor, B. It contains the mechanical properties of the particle and the fluid. Then it depends on the volume B of the particle, on the frequency of the sound wave, on the amplitude, pressure amplitude squared of the sound wave. And here you can see the sinus of 2kx. You see that the force is twice the periodicity of the pressure wave. And yeah, here important is the acoustic contrast factor. It tells you if the particle will go to either pressure nodes, which is the case in our experiment, or it can also go to the antinodes, so the slopes of the pressure curve. So in a microfluidic channel, you have the cross section here, so the channel is in this direction. Here we have a liquid and particles inside. And if we would generate a standing half wave across the channel, it has a nodal plane along the center of the channel, and the particles would be focused in the center of the channel. So in the nodal plane in the center of the channel. Yeah, so my device looks like this. So we have a microfluidic chip made out of silicon and glass, and we made it by standard microfabrication techniques like reactive ion etching and anodic bonding. It contains a channel and 5 cavities with different diameter, so circular cavities. The chip is actuated by 2 piezoelectric transducers here and here, which are on the bottom, attached to the bottom of the chip. And you see the cross section. And we use a thin layer of glycerol as acoustic contact medium. Yeah, at 540 kilohertz, we actuate the chip with also the piezo with a lateral mode. So it looks like this is not a thickness mode, it's a lateral mode. But the polarization is in this direction of the piezo. Okay, so the idea of this design was to have, when we hit the eigenfrequency of a cavity, then particles will be trapped there. And so we could decide on frequency where the particles will be trapped. And in this case, we only had trapping in cavity 3 because only there the resonance of the piezo also matched the resonance, the eigenresonance of a cavity. So if you want to have tapping at other cavities, you may have to use different sized piezo plates. Okay, so our setup. So the chip is mounted in a custom-made chip holder. There we have the piezoelectric transducers here and here clamped between the chip and a thin sheet of PMMA. And we also have integrated fluid connections on the bottom side, so we can mount our chips directly after bonding without any further preparation. So that's quite good for quickly replacing our devices. As tracer particles, we use 20 micrometer big polystyrol beads. And for one experiment, we also use HEC 293 cells. So let's continue with the tapping in the cavity number 3. So here we use generate the 2D standing wave for particle focusing. And in picture A, you see the situation when the transducers are off. We have a flowing fluid containing particles, and the particles are equally distributed if there is no sound actuation. Then when we turn on the transducers, we have particle focusing inside this cavity. So it only takes like 160 milliseconds. And we activate both transducers at 5 or 6 kilohertz. And we continue with the flow, and we collect all the particles. So we trap the particles and collect them all in the cavity. You see the particles continue to get into the cavity, but none of the particles leaves the cavity. This accumulation goes to a certain size. So it is going in this direction, then we lose the particles because here the acoustic force is weak and the streaming profile is fast. So we can only go to a certain size, and after release of the particles, so now we turn on the transducers, off the transducers, the clot is removed, but some particles stick to the surface, so not every particle leaves again. Yeah, and here's a video of the whole situation. So we have continuous flow, nearly continuous flow. Then we focus the particles in the cavity and trap all of them until we reach a certain size. So here, this thing is pushed in this direction, then we lose the particles which are located on the right side. Then we release the sound, so we turn off the sound and the particles are released again, but some adhere to the bottom of the channel. Okay, so here's the situation from outside. It's also nicely visible from outside. And we turn on the trapping, I think now, and collect the particles. Then we turn off again, the particles will be released. And then we turn on once more, now, and again collect the particles. We also tried it out with cells, but cells have a lower acoustic contrast factor, and they're also much smaller. So as you can remember, maybe from the formula above, that the force is depending on the volume. Here we have at least, I think, 50-fold less force. But still we can trap the particles a little bit. Then we apply slight flow and are able to hold the particles slightly, so not so good as before, but still we can hold the particles, but we lose a lot of particles. Yeah, it's a little bit a drawback. So this was our trapping in the cavity, but we also found something else interesting in this device, namely we also found trapping inside the channel, because the discontinuity of the cavities between the channel sections is something like acoustic reflector. So we also can use it. And so we can use it to generate the standing acoustic waves in the channel sections between the cavities. And then we have a standing wave with nodal planes along the channel, and there the particles will accumulate, and it looks like this. So then the question was, can we also trap particle with this? And yes, we can, but when we apply some flow, due to the parabolic flow profile, the particles are pushed to the side walls, and there we don't want to have particles because we don't see it, and they also get stuck. So the solution is, if the particles are pushed towards the side of the channel, we have to push back. So we have the same standing wave along the channel, but now we push back with the second mode, with the second transducer generating a wave that push the particles to the center of the channel, so particle focusing. And if we combine these two, we see that the particles will be very nice focused at the nodal spots in the channel sections too. If we apply some flow, we can also collect the particles, but the force is not as high as before in the cavity trapping. But nonetheless, we can trap particle like this. Here's a video of an experiment. So you will see at first a long side wave generating, and then which have the second actuation, which pushes the particles to the center, and then we will apply some flow. So here's the alongside, and then we push in this direction, and then we apply some flow, and we see we collect the particles, we lose a lot of particles, but on the left side, you can see that there's something growing. If we look closer, we see that there we already have a big bunch of particles, but we also see something we don't want to have as the particle trapping also at the sharp edges here. And we also see the beginning of a Chladni figure inside this cavity. So if you want to have this kind of trapping in a channel, we would have to make a new design. So for conclusion, we were able to do 2D particle focusing in channels and cavities. We trap the particles and hold them against a screen. Drawback number one is we also have trapping at other spots, namely the edges, as mentioned before. And drawback number two, the force on the cells is too weak for effective particle trapping. And the reason for this is that we have relatively low frequencies. And for these small particles, we would need much higher frequencies. So outlook or to-dos for us is, maybe make new designs and decide on our dimensions depending on our target particles. So if we have small particles like cells, we need smaller structures so that we have a higher resonance frequency and thus a higher acoustic radiation force. If we have organoids, it will work like this, I think. Microplastic depends on the size of the microplastic. If we can be able to manipulate vesicles or smaller particles as cells, we need to investigate because our enemy is the acoustic streaming. And the acoustic streaming, you always have it when you generate acoustic wave inside the channel, is proportional to the linear dimensions or to the radius of the particle. And because the radiation force is depending on the volume, so radius squared, for small particles, the Stokes break or the acoustic streaming is becoming much stronger and stronger. Maybe we can use an additional third transducer to have 3D particle focusing, so we also generate the wave in vertical direction. If we would use different transducers, we would be able to have the particles dependent on the frequency in the different cavities. And if we would use more amplifiers, then we would also be able to have a stronger particle trapping inside the channel sections, because here we use 2 different frequencies and we had only 2 transducers, so we had less power than in the cavity trapping. So thank you for the attention.